Objects that are spinning have kinetic energy associated with that motion, plus the kinetic energy associated with the motion of their center of mass through space. For an object that rolls without slipping, those two are connected because V equals R omega. So we can write K is a half mv squared plus a half I omega squared. But remember that omega is V over R. So we can say a half mv squared plus IV squared over 2R squared, or a half mv squared plus a correction factor. Notice that since this is always positive, rolling at any given speed has more energy than if it were simply sliding at that speed. Let's do an example. Take a hollow ball. A hollow ball has a rotational inertia which is 2/3 m r squared. So what is the kinetic energy of such a thing? Well, if we walk through, 1/2 mv squared plus 1/2 I omega squared, but I is 2/3 mr squared. And notice that now the r squared and this r squared are going to cancel. And so we get that it's 5/6 mv squared. Notice it doesn't depend on how big the thing is, which is kind of weird. And we'll see that keeps coming back as a weird output here, is that the size of the rolling object will drop out a lot of the time. Not always, but a lot. Let's talk about how high will it roll up an incline. Well, at the top of the incline, it is at rest, both in translation and in rotation. We can use energy conservation. That kinetic energy that we found here has to turn into gravitational potential energy when it gets to the top. Then we just do some calculations. 5/6 mv squared becomes mgh, so h is 5v squared over 6g. All right, this is our situation here. Let's compare that to a block that slides up a frictionless incline but isn't rolling. So a block, same mass, moving at the same speed, but it just slides up because it can't roll. Then we have a half mv squared over here instead of 5/6 mv squared. We still have mgh height. Now, I put mgh star because there's no reason to think that these are the same height. And in fact, h star is v squared over 2g, which means since 5/6 is more than a half, we end up that the height this has is more than the height that this reaches. They were not equal. The ball rolls higher than the block slides. Why? Because it has more energy to tap. It started off with more kinetic energy, and all of that's turned into gravitational energy, so it goes higher. Of course, in the beginning of the problem, somewhere out here, it took more work to get it going up to that speed, but that's what we were interested in. What about friction? Did you notice the slide subterfuge? I used energy conservation, but for the ball to roll, there must be friction. Otherwise, it can't roll without slipping. Things can only slip on frictionless surfaces. Friction plays an interesting part in rolling. To be without slipping, the point of contact must be at rest. That's what it means to be not slipping. But if it's at rest, it has a velocity of 0. And if the velocity is 0, then the power delivered by friction is 0, because the power, remember, is F times V. And so the work done by friction is 0. So for rolling objects, friction does not dissipate any energy into heat. We can apply energy conservation even though there's friction. It has some interesting roles here. In fact, what friction ends up doing is keeping things at some constant velocity, if the object, and we should always stress this, is rolling without slipping. Let's return to the earlier ball. Let's start it rolling on a rough surface, but then transition to a frictionless surface, and then up a frictionless incline. Once it's on the frictionless surface, there isn't any coupling between V and omega. So it rolls along here until it reaches this point, and now it is going to be sliding, essentially, all the way up here. Once it reaches the frictionless surface, even as V decreases, the rotational speed stays the same. There's nothing coupling it that could be taking away rotation. There's no friction here that would be able to spin it down. And as such, the height ends up being V squared over 2g, the same as the sliding block. Why? Well, there is energy locked up in rotation. It remains locked in rotation. It's unavailable to us. So it ended up dropping out of the equation, and we get the same height, just turning the translation into gravitational potential. All right, let's try this problem. A thin hoop or ring with a radius 2 meters is moving so that its center of mass is initially moving at 20 meters per second while rolling without slipping at 10 radians per second along a horizontal surface. Couple things. One, just to remind you, a thin hoop or ring the inertia is simply mr squared. Second, it was a little goofy that they told us that it was moving at 20 and rolling without slipping at 10 rad because V equals R omega, so it had to be that way. That was redundant. Now, it rolls up an incline coming to rest as shown. Complete the qualitative energy bar chart below for the Earth hoop system for the time when the hoop is rolling on the horizontal surface and then when it has rolled up the ramp and is momentarily at rest. Let's do some easy parts first. Hey, there's no spring, so obviously potential energy of the spring is 0. And at the top, we're told that it's at rest, so those kinetic energies are 0. And there's no external forces acting on it, or at least doing any work, so there's no work done there. They tell us that this is going to be y equals 0, so there's no gravitational energy. The key thing here is how much rotational energy is. So we say, well, the rotational kinetic energy is 1/2 I omega square, 1/2 mr squared times v over r quantity squared. The r squares cancel. We get 1/2 mv squared. Hey, that's the same as the translational energy. So whatever we had here goes like this. And then since no work is done, the energy here has to equal the energy here, but there's only potential energy left. So if there were 4 and 4, there must be now a total of 8. And so our final chart looks something like this. A solid sphere rolls without slipping along a track shaped as shown at the right. It starts from rest at point A and is moving vertically when it leaves the track at point B. At its highest point while in the air is the sphere above, below, or at the same height as point A. On the way down, friction is allowed to spin up this thing, so it picks up all of this gravitational energy and it turns into rotational and kinetic energy down here. But once it leaves the track, it can't access that rotational energy. So there's less energy. Some of the gravitational energy here cannot be turned back into gravitational energy here, and so it will end up being below where it had started. Four objects are placed in a row at the same height near the top of a ramp and released and rest at the same time. And the objects are a 1 kilogram solid sphere, a 1 kilogram hollow sphere, a 2 kilogram solid sphere, and a 1 kilogram hoop. All four have the same diameter, and the hoop has a width that is 1/4 its diameter. The time it takes the objects to reach the bottom is recorded, and then they give us the moments of inertia, and they ask us to draw a blue circle around the objects that take the shortest time, and a red object around the objects that take the longest. So the shortest are the ones who win the race. Well, one way to look at this is that we're going to be turning gravitational energy into rotational energy and translational energy. But the more of it that's in rotational energy, the less is available for translational energy, so the slower we're going, and the slower we're going, the longer we'll take. So the thing that has the most fraction in rotational stuff is going to be the loser, and the one that has the least is going to be the winner. Well, the loser is therefore going to be the hoop, because the hoop has the most inertia, and so it's going to carry, at any given speed, it's going to carry more of its energy in spinning compared to others for the same initial energy. The fraction will be larger, more in spinning. And then the spheres, the solid spheres are going to be the winners because they will spend as little as, fractionally, they will spend as little as much on rotation and therefore more of them on translation. On the next screen, I'm going to go through and do this a little bit more quantitatively in case that kind of fuzzy thing was not your game. All right, so let the mass of the thing be m, the radius be r, and the rotational inertia be I, but let's represent I as k times mr squared. You might have noticed they're always something times mr squared. So k is a factor that depends on the type of object. For a solid sphere, it's 2/5. For a hollow sphere, it's 2/3. For a hoop, it's 1. Released from rest at a height h, all of the initial GPE is turned into kinetic energy at the bottom, so mgh becomes a 1/2 mv squared plus a 1/2 I omega squared. But I, remember, is k times m times r squared. So we get mgh is 1/2 m times 1 plus k times v squared. Hey, look, the M drops out. That's not surprising. So it doesn't matter whether it's the heavy solid sphere or the light solid sphere. They'll have the same behaviors. And we know that for all the objects, these are the same number. So a larger k factor means a lower v, which is what we have for any height. This is in fact true at any height. It must be the larger k produces a smaller average speed, which means it will take the longest when it has a large k. So the solid spheres take the same time and they take the least. The hollow sphere takes a little bit longer, and the thin hoop takes longer than that.